Get ready to blow your mind. All three forces, whether it's Coriolis force, or centrifugal force, or centripetal force, are connected to this one powerful idea. Once you truly get it, these seemingly strange forces will start to make perfect sense. So whatever you do, don't skip this. Imagine a person standing at the center of a bus with a perfectly smooth, frictionless floor, similar to standing on a super smooth ice. Now suppose I am an observer standing on the ground, watching the bus and the person inside it. This ground is not accelerating, so it is called an inertial frame of reference, which is a fancier way to say that the surface on which I am standing is either at rest or moving at a constant speed in a straight line, and is not accelerating. In an inertial frame of reference, Newton's law, force equals mass times acceleration, or F equals m times a, applies exactly as stated without needing any modifications. Let us now set up a coordinate system. Suppose we fix an x and y axis on the ground with the center of the bus at the origin, that is at x equals 0 and y equals 0. The person is also standing exactly at the center of the bus. Now suppose the bus suddenly accelerates to the right with some acceleration a, and there is no friction between the person and the bus floor. After 1 second, from my point of view, as an observer on the ground, the person did not experience any force, so for the person, force is 0. So by Newton's law, acceleration is 0. That means the person stays at the same position x equals 0. However, the bus has acceleration a, and it moves forward. Since the motion is from rest, we use the formula x equals half times a times t squared. So, after 1 second, the center of the bus is at x equals 0.5 times a. So, from the ground view, the person is still at x equals 0, but the bus center is now at x equals 0.5 a. This makes sense because the person did not have any force, so it stayed at the same place. But the bus did have a force, so it moved. Newton's law works correctly here because we are in an inertial frame. Now let us change the story. Suppose now I am inside the bus, which means the observer who was looking at the person and bus from the ground is now inside the same bus and is accelerating along with the bus. Also, my coordinate system is now attached to the center of the bus. That means wherever the bus goes, my x and y axis also go along with it, and my xy axis will accelerate along with the bus. This kind of moving frame, which is accelerating, is called a non-inertial frame of reference. Now let's see what happens in this case. We again start with both the person and the center of the bus at coordinate x equals 0 and y equals 0. But now, since I have tied the axis to the bus, when the bus accelerates, my axis also accelerates. So, after 1 second, the bus center will still be at x equals 0. But when I look at the person from inside the bus, I feel like the person moved backward. Using the same formula x equals half times a times t square, I will say the person's position will be at x equals minus 0.5 a. So now, from the view inside the bus, the center is at x equals 0, and the person is at x equals minus 0.5 a. It looks like the person moved backwards. But here's the twist. Newton's law force equals mass times acceleration does not work directly here, because this is a non-inertial frame. This is because the bus, from our point of view inside it, is at rest and not accelerating relative to us or the observer. Also, from inside the bus, since there is no friction between the person and the floor, there is no force acting on the person. So we say F equals 0 for the person. Yet, we see the person slowly moving backward, even though no force seems to act. To fix this, we introduce something called a pseudo-force or fictitious force on this person. This is not a real force, but we add it just to make Newton's law work in this accelerating frame. Since our xy axis, or the frame of reference, is accelerating forward with acceleration a, we apply a pseudo-force in the opposite direction, that is backward, with magnitude m times a on the person. So now, it looks like the person has a backward force, so it moves backward with acceleration a, and we can say F equals m times a still holds in the bus frame, but only because we added this fake or pseudo-force. If this is clear, then we can now easily understand Coriolis force, centrifugal force, and centripetal force. Imagine a large circular platform lying flat like a giant disk. Let us fix the center of the platform as the origin of our coordinate system. Now, let there be a point C painted on the platform. This point lies at a fixed distance from the center, say r units away, along the positive x-axis. So its coordinate is x equals r and y equals 0. Also, imagine a person A standing exactly at the same location as point C, that is, at position x equals r and y equals 0, at time t equals 0. There is no friction between the person and the platform, and the person is not holding on to anything. Let's now fully describe what happens from the inertial frame of reference, or the observer standing on the ground. As the platform starts rotating counterclockwise with angular speed omega, the point C, being painted on the surface, continues to follow the circular path. So after a small time, say 1 second, point C will have rotated through an angle omega radians and moved to a new location given by x equals r times cos of omega and y equals r times sine of omega. But what happens to person A? At the very instant the platform starts rotating, the point C beneath their feet begins moving in the y direction, and the person gains an initial velocity in that direction due to being momentarily in contact. That velocity is equal to r times omega, pointing in the positive y direction. Since there is no friction and the person is not holding on to anything, there is no force acting on the person. And Newton's first law tells us they will continue to move in a straight line with constant velocity. So after 1 second, their new position is x equals r and y equals r times omega. That is, they have moved straight up while the platform has rotated underneath. Person A is at x equals r and y equals r times omega, which lies just outside the circle and almost in a straight line with the origin and point C, especially if omega is small. This shows that in the inertial frame, person A begins to drift outward, and this also proves a deep point. For person A to stay at point C and continue moving in a circle, a real force would have been needed pointing inward, pushing point A toward the center. This force is called centripetal force, which is a real force in the inertial frame that is required to keep an object moving in a circular path by constantly pulling it inward toward the center. This can either be a friction force or a tension in the string or any other physical force providing the inward pull. Now, if our xy axes themselves rotate with the platform, which means our observer is now in a non-inertial or rotating frame of reference, then things look very different. At time t equals 0, x and y axes are like these, and both point C and person A are at position x equals r and y equals 0. Even after some time, point C continues to stay fixed at the same xy coordinate from the rotating frame's perspective, because it is painted on the platform and simply rotates with the axes, and we will see as if it is not moving at all. However, the person A, who is not attached and feels no friction, does not follow this rotation. From the rotating frame's view, for a small time interval, it will look like the person is sliding away from their original position on the circle in the radially outward direction. This seems strange because both point C and person A were on the platform, and our observer is also standing in the rotating frame. So, it should feel like neither point C nor person A is moving at all. This means that, from the rotating frame, both point C and person A should have zero acceleration. That's why point C does not change its position and stays at R, 0. But we can see that the person A is drifting outward, so it's not clear why the person suddenly starts moving outward. To explain this, we introduce fictitious forces in the rotating frame. Forces that are not real, but must be added to make Newton's law work. Since the person is moving outward in this rotating frame, we say a centrifugal force is acting on them, pointing away from the center. Its magnitude is m times r times omega squared, where m is the mass of the person. This force is not real. It is only needed to make the person's apparent outward motion make sense in the rotating frame. Now let us understand the Coriolis force. Assume a circular platform, which is not rotating at the moment, and this is point C at the edge of the platform. Then suppose you keep a ruler and try to draw a straight line from the center of the platform to this edge, or point C in this case. This blue ball will be the position of your hand as you draw the line, and this vector is the ruler. And since the platform is not rotating, your hand will simply move along the ruler in a straight line from the center to point C without any deviation. But now, when the platform starts rotating in counterclockwise direction, things look very different. Look at this animation. As you try to move your hand in a straight line from the center toward point C, the platform starts spinning underneath. It looks like your hand is curving away along with the ruler, drifting to the side. The ruler, which will rotate in the opposite direction of the platform, and the blue ball is the position of your hand, which always stays on the ruler. This is the curve that you will end up with. Try it out at your home. It will feel as if some invisible force is pushing your hand sideways. This apparent sideways deflection is what we call the Coriolis force. Suppose you and your friend are sitting on opposite ends of the merry-go-round. You try to throw the ball towards your friend, but he will never be able to receive it, because from your rotating point of view, the ball curves away as it travels. Even though you aimed straight, the ball appears to bend sideways and miss him. This bending is not due to any real force acting on the ball. It's just how things look when you're in a rotating frame, and that apparent curve is exactly what the Coriolis force explains. Note that this deflection of the ball will be seen by you and your friend because both of you are an observer sitting in the rotating frame. For a person observing the ball from the ground will see the ball moving in a straight line, because for a person in the inertial frame, the ball simply follows Newton's first law, that is, it moves in a straight line at constant speed unless acted upon by an external force. Since no force is acting on the ball after it is thrown, it continues in a straight line. So you will have to adjust the direction in which you throw the ball, not straight at your friend but slightly off to the side, so that the ball curves during its flight and still reaches them. The value of this Coriolis force is -2 times the omega cross v, where omega is the angular velocity vector of the rotating platform, and v is the velocity of the object as seen in the rotating frame. Now, if you throw the ball toward your friend in the positive y direction, which means v is in positive y direction, and because the platform is rotating in counterclockwise direction, so using the right-hand rule, omega will be in the positive z direction, then omega cross v will be in the negative x direction, and thus the direction of the Coriolis force will be in the positive x direction, like this. This means the ball will appear to deflect toward the right side of its path in the rotating frame. Can you share any other real-life examples of the Coriolis force in the comments? If you enjoyed this video, please don't forget to like, share, and subscribe